Hello, I'm Lionel Malbec, Senior Product Manager at ArcticZymes Technologies, and today I'm pleased to walk you through our new poster about how your nuclease strategy can unlock process and cost efficiency. Today, more than half of the produced vectors is lost during downstream processing, and this is one of the major barriers to cost-efficient viral vector manufacturing. But one factor that can directly impact this challenge is your nuclease strategy. So now let me show you why. Let's start with the problem. Chromatin is the dominant contaminant in viral vector manufacturing, and it's difficult to digest. Why? Because chromatin is not free DNA. It's a complex of DNA tightly wrapped around histone proteins. And that structure makes it highly resistant to standard nuclease treatment. And that brings me to the core technical issue. Conventional nucleases lose activity under process-relevant conditions, and the major challenge is salt. Most lentiviral and AAV processes run at physiological and high salt conditions, conditions where standard nucleases simply don't perform. Salt-active nucleases solve this issue. SANHQ is engineered for high salt conditions, while mSANHQ is optimized for physiological salt conditions, making each of them the right tool where you need efficient chromatin digestion. So now let's look at what happens when chromatin isn't properly digested. It's aggregating, leading to filtration membrane clogging. The outcome is that you get a reduced recovery yield and batch-to-batch variability. But most critically, you are underestimating the DNA contamination levels. That can lead potentially to a regulatory challenge. As you can see in this TM image, as well as in this Western blot data, courtesy of our collaborators at ACIP, you get some leftover chromatin aggregates upon conventional nuclease treatment. That co-purify with your vector during chromatography steps. This directly reduces the yield and purity of your production. With SANHQ and mSANHQ, chromatin is highly efficiently digested. Small fragments are trapped into the resin during chromatography, so they don't coelute with your vector, which end up clean. And so the result of this is a 10-time improvement in DNA clearance, a 70% reduction in downstream processing time, as you don't need additional nuclease treatment steps, and a 2-time higher recovery, with 4 times less nuclease consumption per batch. And when you translate all of that into economics, the numbers are compelling. Adapting your nuclease strategy can deliver more than 70% reduction in nuclease cost per batch. That can lead to more than 40% reduction in total COGS per dose and end up in $15 million USD in annual COGS savings, modeled on the 2,000 liter scale, 50 batch per year scenario. So it's clear that your nuclease strategy has a significant process and cost impact. And so the real question for you is, what could changing my nuclease strategy mean for my next therapy?